All right, let's talk about a huge shift happening in the world of software right now. It's this massive search for what's called memory-safe code. And this isn't just about making your apps a little bit better. No, this is about securing our entire digital lives. So let's dive right in. And when I say high stakes, I'm not kidding. This whole debate has literally jumped from developer forums all the way up to the highest levels of government. We're talking about the White House. Back in early 2024, they put out this really clear directive, basically telling the entire tech industry, hey, you need to adopt memory-safe programming languages. The message is loud and clear. The way we've been doing things is creating way too many security holes. So why all this pressure from the top down? Well, the data, it paints a pretty stark picture. Okay, check out this number. This comes straight from Microsoft's own analysis. They looked at their security bugs and found that a whopping 70% of all their vulnerabilities were caused by memory safety issues. Think about that. These aren't just some obscure minor problems. They are the single biggest cause of security flaws. And this isn't just a Microsoft thing either. Over at Google, their research found that 68% of what are called zero-day exploits, and these are the really nasty ones, the most dangerous and valuable hacks out there, are directly tied to memory corruption. This is the absolute root cause of some of our most critical security breaches. So what are we even talking about when we say memory safety? Well, to put it simply, it's about a language's ability to stop a program from messing with memory it's not supposed to touch. Things you might have heard of, like buffer overflows or dangling pointers, honestly, they're like leaving the key to your house right under the doormat for a hacker. They're the cracks in the foundation of our digital world that attackers just love to exploit. All right, so for decades, the undisputed king of high-performance systems programming has been C++. I mean, this is the language that powers everything, from your computer's operating system to the biggest video games. And it's all built on this one core philosophy: ultimate freedom for the programmer. The whole idea behind C++ is basically we trust the developer. It gives you mind-blowing speed because it lets you manually control every little detail of the computer's memory. But all that power, it comes with a huge price, an enormous amount of mental overhead. See, the developer is responsible for getting everything perfect, and the language itself, it won't lift a finger to stop you from making a really, really catastrophic mistake. And this philosophy, this idea of just trusting the programmer with all these low-level details, has led to what one of the pioneers of computer science, Tony Hoare, famously called his billion-dollar mistake. It's this long legacy of memory errors that are super easy to create, but incredibly hard to find. And that is exactly what the White House is trying to fix now. So let's walk through a classic C++ trap to see what this looks like in practice. Imagine you've got a vector. It's just a list of items that can grow. Okay, so we have a reference, basically a pointer, that's aimed at one of the items inside that list. Simple enough, right? But here's the catch. What happens when we add a new item to the list? Well, the list might need to move somewhere else in memory to make more room. And just like that, our original reference is now dangling. It's pointing to an old, empty spot. If you try to use it, boom, that's a critical bug. And the scariest part, the C++ compiler will just let it happen without a single warning. Okay, so now let's talk about the challenger that's really sparked this whole conversation, Rust. It was designed from the absolute ground up with a totally different philosophy, specifically to solve the very problems that C++ often creates. See, instead of just trusting the developer, Rust's whole philosophy is to make the developer prove to the compiler that the code is safe. The goal here is to guarantee memory safety before the code is even finished compiling, which completely wipes out entire categories of bugs before the program can even run. And here's the magic of how it works. Rust pulls this off with two core concepts. First, you have ownership. Every single piece of data in Rust has one and only one owner. And when that owner is gone, the data is automatically cleaned up, no leaks. Second, you have borrowing. This lets you grant temporary, controlled access to that data. But, and this is the key part, only under a really strict set of rules that the compiler enforces. Okay, so let's replay that dangerous C++ scenario, but this time in Rust. We try to do the same thing. We want to modify the vector to push a new element onto it, while we're also holding a reference to an item inside it. The Rust compiler sees this immediately. It knows that pushing a new item could invalidate that other reference, and so it just refuses to compile the code. The bug is stopped dead in its tracks, before it was ever even born. And what's so powerful here isn't just that the Rust compiler stops you, it's how it stops you. And this really gets to the fundamental difference in their whole approach. Instead of some cryptic error code, the Rust compiler basically acts like a friendly teacher.
It gives you this super detailed error message that explains, hey, you can't have a mutable borrow here, while an immutable borrow also exists. It points you to the exact lines of code causing the problem and explains the ownership roles you accidentally broke. It literally helps you learn how to write safer code as you go.
And this quote here from the FreeBSD mailing list just hits the nail on the head. It's a decision about human behavior. Rust makes safety the default. It's not some optional warning that you can just ignore or turn off. It's a hard wall. If your code isn't provably safe, it simply will not build, period. Now, as you can imagine, this huge paradigm shift has not gone unnoticed. The C++ world, with its decades of legacy code and this massive ecosystem, is now trying to figure out how to respond. And a really big effort is underway for the C++ 26 standard. It's a proposal for something called safety profiles. And the whole idea here is to basically retrofit some of Rust's compiler-enforced safety guarantees directly into the C++ language itself. So what these would be are basically opt-in modes for the compiler. A developer could choose to turn on a profile for things like checking array bounds, ensuring type safety, or managing object lifetimes. The goal is to enforce these stricter rules without breaking the 4 decades of backward compatibility that C++ is so famous for. The vision here is pretty cool. The idea is that developers could take millions of lines of existing C++ code, flip a switch to recompile it with one of these safety profiles turned on, and then have the compiler automatically find and diagnose bugs that have been lying dormant and silent, maybe for years. It's a really ambitious attempt to evolve safety into an already massive ecosystem. And that really leaves us with this fundamental question for the future. On one side, you have C++ trying to evolve, trying to layer safety on top of a massive and, battle-tested foundation. And on the other side, you have Rust, which just started over from scratch to build safety into its very DNA. These two paths, they represent the central debate about how we're going to build the truly secure software of tomorrow.